the recording. No, I can't share screen. Okay. All right, so today's talk will be some background and a bit of motivation on the topic of special values of L functions, starting with the topic of what L functions are in the first place. So I will start by writing down the function which should be familiar to most of you, which is the Riemann zeta function, which is defined as the sum from n equal to 1 to infinity of 1 over n to the power of s. And here s is some complex number. And this makes sense if the real part of s is strictly greater than 1. This function can be analytically continued to other values of s, but this is not something we'll need for today's talk. And this function is arguably one of the most important functions in all of number theory, and specifically in studying properties of prime numbers. And the reason for that, something which connects the prime numbers to the analytic world, is the fact we can rewrite this function as a product over primes. So such a product like this, product P will always be over prime numbers. And the factors are 1 minus 1 over P to the S, and it's the power of minus 1. Again, in this range here. This you can see by expanding this as a geometric series and then multiplying out the product. And this kind of expansion and working with the zeta function is, for example, something that is pretty much crucial to working out things like the prime number theorem. But if we want to study some deeper properties of primes, for example, not just their total distribution, but how they are distributed modulo some number, for instance, then we need to introduce some other similar functions like this. And the class of functions which are very useful for that are the Dirichlet series. So those are series of the form sum an over n to the s, again over also same bounds, where an are some constants which belong to complex numbers. And if we want these to be related in the same way to prime numbers like the Riemann zeta function was, we would like this sum to also have some kind of product expansion over primes. Such an expansion is also called an Euler product. And the way this is done, so this will not always exist. For this to exist, we need to assume that n satisfies some extra properties, specifically multiplicativity. And I will assume something stronger than them, namely, we'll be interested in ones which are totally multiplicative. So we assume that those coefficients here, an, satisfy a and m is equal to an times am for n for O and m. And in that case, we can write that this sum an over n to the s can also be written as such a product over primes of 1 minus ap over p to the s to minus 1. And you can show it in a similar way. One of the more important classes of such sequences of coefficients is given by Dirichlet characters, which are additionally given, which additionally satisfy the property that the sequence is to be periodic. So we introduce the definition. Dirichlet character is a function which is usually denoted by chi, from the integers to complex numbers such that first of all, it is totally multiplicative. In the sense that it satisfies this condition here. It is periodic with period m, which is some natural number. And we also have one extra condition, namely that chi of n is equal to 0 if and only if GCD of nm is greater than 1. So this function is non-zero precisely on numbers which are coprime to this period m. We just call them modulus. So this is called the modulus. Okay, and for such a function, we can consider the Dirichlet series with those coefficients, and we define Dirichlet L series or L function, which is L of chi of S, is given by a sum of chi over n over n to the power of s. Whenever this makes sense. It turns out that in non-trivial cases, this makes sense whenever s has real part, which is positive, not necessarily greater than 1. Okay. And those functions, they are very important for studying primed in arithmetic progressions. And of particular importance is the value L of chi 1, just at the point s equal to 1. And specifically for Dirichlet's theorem, which guarantees that there are infinitely many primes in every arithmetic condition, arithmetic progression, those elements are coprime to the modulus, relies on the following theorem. Which says that for any non-trivial chi, so non-trivial here means that chi isn't just constant 1. We have L of chi 1 is not equal to 0. So this is something, so this value does not vanish. So the Dirichlet L functions never vanish at the point 1. Okay. So, but if this value is non-zero, then we can wonder what exactly this value is, and if maybe this value can tell us something more interesting about some arithmetic structures, like those primes. So for simplicity, and because this is where most interesting arithmetic will be happening, I will be restricting to characters called quadratic characters. So quadratic characters. Which means that chi of n will belong to 1, 0, or -1. So it will be non-trivial, but it can only take value -1 apart from 1 and 0. Okay. And in this case, there will be some, most of those characters are essentially going to be determined by the quadratic reciprocity symbols or Legendre symbols. So in particular, so actually I write this in a second. We write chi of d of p. So sorry, chi of d will be the is the character determined by chi of chi d of a prime is supposed to be the value of d on p. This is the Legendre symbol, and by definition, it means that this is 0 if p divides d, it is 1 if d square mod p, and -1 otherwise. So in this case, it's not clear that this is periodic. This is something that is guaranteed by this quadratic reciprocity law that I just mentioned. And we'll be also putting some restrictions on D, namely that here D is square free, square free odd number, or D is equal to 4 times odd square free number. I will briefly mention why we put this condition here later on. Okay, and now, and D is some integer, and which is not necessarily positive. So will have either D is positive or D is negative. And this actually gives us, lets us split this into 2 different cases. So case 1 will be if D is negative. So in this case, it turns out that the value L of chi D1 is going to be equal to some rational multiple of pi divided by square root of the absolute value of D. And this here is not very difficult to establish, but exactly what this rational multiple is much more interesting, and we do know this exactly as well. So let me write this as a theorem. For D less than 0, we have L of chi D at 1 is equal to 2 pi divided by square root of D times HD divided by W of D. And what are those 2 quantities, H of D and W of D? W of D is easier to explain. So we have where WD is the number of roots of unity in the field Q adjoint square root of D. And we can even write explicitly what it is. So it is going to be 4 if D is equal to -1, because there we just have the square root of D, which is I, minus I, we have +1 and -1. It is going to be equal to 6 if D is equal to -3. There we can have, in Q adjoint this root -3, we have the cube roots of unity. And then in all other cases, we have exactly 2 roots of unity. If D, so if D is less than -3. So this is a relatively simple, albeit a bit weird quantity. Now h of d is going to be more interesting because this turns out to be equal to the class number of the string of integers in this field q square root of d. I will not explain precisely what this class number is, but I will briefly explain what it means in one specific example. So we shall take d to be equal to minus 20, in which case this field here, which I'll call k is equal to adjoint root of minus 20, or we can just write it as q adjoint root minus 5. And in this case, we can explicitly compute that L of k d at 1 is equal to 2 pi over square root of 20. And in here, we see that this should be, using this theorem above, this should be equal to square root of 20 times h of d and w of d. So we know what wd is in this case. It is going to be equal to 2. And this tells us that hd must also be equal to 2. So this gives us that hd is equal exactly to 2. So what does this class number tell us? So the fact that hd is greater than 1, this corresponds to the fact that if we consider the ring z adjoint square root of minus 5, then this is not a unique factorization domain. So in some sense, this class number here is a measure to what extent this ring fails to be a unique factorization domain. If it is equal to 1, then we have unique factorization, and in fact, this is going to be a principal ideal domain. If it is strictly greater than 1, then some ideals will come into non-trivial classes of not being principal, and this hd measures how many of them there are. So it being equal to exactly 2 tells us that there's not a principal ideal domain, but it is almost one in an appropriate sense. Okay, so that was the case for the negative. And now we also have the second case, where d is positive. So in this case, of kd also relates to arithmetic of the field of k, which is this q adjoint square root of d. And in fact, it also involves the class number, but it will also involve another quantity. So in the previous case, the other quantity that was relevant was this number of roots of unity in this field. In here, it turns out that this field for d positive will not contain any roots of unity apart from 1 and minus 1, because it consists only of real numbers. But it will contain some, but the string of integers that we mentioned above will contain some non-trivial units. And in fact, if we consider in the ring of integers, which is denoted O of k, we'll have that, okay, the set of units is going to consist of plus minus 1, and it will be a product with an infinite cyclic group, which is generated by a single element. So I write it as epsilon to the n, where n is in Z. And as much as it pains me, as it will you, epsilon here is a standard notation for an element which is greater than 1. So this is not to be thought of as an epsilon from analysis, which is very small and close to 0. And this epsilon here is called the fundamental unit. And in this case, the theorem takes the following form. For d greater than 0, L of chi d1 is equal to 2 divided by square root of d. So similar as before, except without this pi here. And now we will have the class number as before, and we will also have the logarithm of this fundamental unit epsilon. So let me maybe try to explain a little better what this looks like by again considering an example. We shall take d to be equal to 3. And in this case, O of k is going to be just the ring of integers, the adjoint square root of 3. And in this case, the group of units, it is going to have plus or minus 1. And the other non-trivial units are going to be given by powers of the element 1 plus square root of 3. No, sorry. 2 plus square root of 3. I have to fix that in my notes. To the power of n, where n is in Z. And where does that come from? So why is this a unit? This is because if we take 2 plus root of 3 times 2 minus root of 3, which is obviously also in this ring, this gives us 2 squared minus root 3 squared, which is precisely equal to 1. So this is indeed a unit. And with some pretty elementary arithmetic, you can show that there are no other units apart from ones of this form. And in this case, the value here is going to be given by 2 divided by root 3. The class number in this case is equal to 1. So this is not a problem. It's not a factor we have to consider. But it will be multiplied by the logarithm of this fundamental unit, 2 plus root of 3. Okay, so we have now formulated this theorem into different cases when d is negative and d is positive. Those are classically called the class number formulas. The point being that they express the class number, 8 of d, in terms of some other quantities, which in some cases might be easier to compute or easier to study in some ways. And this is something that can be generalized quite substantially, but we have to extend, we have to quite thoroughly extend the kind of structures, the kind of L functions that we are considering. So Dirichlet L functions are the ones which give us the behavior of quadratic extensions in a sense. So another thing I want to talk about is what we can do for an arbitrary number field, namely, which is closely related to the Dedekind zeta function. So in this case, we have let K be an arbitrary number field, which is just some finite extension of the field of real numbers. And in this case, we can consider, O of k again is a string of integers. And we can write the Dedekind zeta function of S. We can write it as follows. So it is a sum over non-zero ideals of ideals I of O of k. And the sum has terms 1 over the size of O of k divided by I to the power of S. So if we take k to be the rational numbers, then O of k is integers. And in this case, you can see that this just gives back the Riemann zeta function. But for general number fields, it is going to be much different. And also let me mention that even though it seems to be written in quite a different way than what we had before, because we are summing over those ideals, it can also be written as a Dirichlet series of Cn over n to the s, where Cn is the number of ideals I such that OK over I is equal to n. So we're basically just grouping terms, and one can, without much difficulty, show that this quantity Cn is finite. So we have, we can write this as a Dirichlet series like this. All right. So when k is a quadratic number field, oops. Number field. Of the form key adjoint square root of some element, then we can show that this eta k of S is going to be a product of the usual Riemann zeta function. And also we have a factor of L of k of D S, which is this Dirichlet function that has appeared before. So we see that this Dirichlet L function also appears in a sense in the Dedekind zeta function. And this, the value of the cell function at 1 can be translated into the residue of the pole of this function at s equals to 1. So this means that class number formula tells us residue of zeta k at s equal to 1. And the general class number formula is a similar statement, but it holds for an arbitrary number field. So let me state this theorem. Okay, number field. Then residue of zeta k at s equal to 1 equals this very funny quantity, which is 2 to the power of r1 times 2 pi to the power of r2 times reg of k times h of k divided by w of k times square root of dk. Now, I just wrote a lot of symbols, so let me explain what those are. So R1 and R2, they are related to the they are the number of ways in which this number field k can be embedded into the field of complex numbers, where R1 is the number of ways in which it maps into the real numbers. So R1 is equal to the number of embeddings from K into R. And R2 is similar, but for other embeddings, those which don't land in real numbers. So specifically pairs of such embeddings. So 2R2 is equal to the number of embeddings K into C not contained in R. This regulator, actually, let me explain this at the end. This HK here, HK is equal to the class number of K. WK is the number of roots of unity in K. DK, this is the discriminant. Of K, which I will not define here, but this discriminant is, those discriminants are, sorry, let me rephrase. So the numbers that we have restricted to earlier on, when I said it is either square-free odd or 4 times square-free odd, those are the numbers which appear as discriminants of those quadratic number fields. So our restriction was there so that when we take the discriminant of the resulting number field, the result is exactly this number D that we put in. Okay, and now the regulator. So this is a quantity. Yeah, this is the quantity called the regulator, and it measures. I put this in quotes. Measures how dense units are in O of K. So in particular, this directly generalizes this log of epsilon that we had before, in the sense that the larger this quantity is, the sparser the units are in this ring in an appropriate sense, which I'm not making precise. Okay, so this means that, and in general, all of those quantities are much easier to compute than the class number itself. There are some issues with the regulator, but they can often be dealt with much more easily. So those give us, in many cases, a way to deal with the to express this class number here in analytic terms using this residue of this Dedekind zeta function. Okay. So this is more or less what I had prepared for this talk. So this talk was supposed to be is meant as a preparation for the talk which my advisor will be giving right after me, where she will be also talking about the relation of this to the Bertrand-Swinnerton-Dyer conjecture. But because you will not be there for her lecture, let me say at least a few words about the way in which this extends, or rather than extends, how it can be related to this Bertrand-Swinnerton-Dyer conjecture. So this Dedekind is, so these Dirichlet L functions and this Dedekind zeta function that we consider, those are objects which can be, those are analytic objects that can be related to the number field, to just arbitrary number field. And it turns out that in many cases, we can associate such analytic functions from Dirichlet series to other objects of interest in arithmetic geometry. And the simplest example of such a let me say non-trivial such arithmetic object is an elliptic curve. So we have some elliptic over let me say over rational numbers. So let me call it E. And in this case, if we have it defined over E, it can be written by given by an equation of the form y squared is equal to x cubed plus ax plus b. And let me assume that a, b are integers. In general, they are rational, but we can always rescale the coefficients appropriately. And if those coefficients are integers, then we can also consider the reduction of this curve modulo primes. So for any prime, p, let me write this as E of fp. There's a bit of an abuse of notation here, but this is meant to be the not just the number. This is supposed to be the set of solutions. Oops. With x, y in fp squared. So in particular, we only require this to be a congruence mod p, not an equality. And let me define a bit of a funny quantity, which is AP, which is equal to P minus the size of this FP. I'm also ignoring the point at infinity, if anyone knows what that is. So we have those quantities AP. And now we can introduce another Dirichlet series, which is called the Hasse-Weil L function of this elliptic curve, as follows. So I'm going to introduce it directly in terms of a product over primes instead of as a usual done as a sum. This is a sum over product over 1 minus AP, AP P to the S plus 1 over P to 2S minus 1. It shouldn't be too hard to convince yourself that you can expand this series to get some expansion in terms of a sum like in usual Dirichlet series. And this to the power of -1, yeah. And yeah, so this is an L function which is built completely out of, in a sense, local information about our elliptic curve, because these AP only depend on the reductions of our field, of our curve modulo FP, and we are only counting the rational, the points over those fields, as opposed to integer or rational points. However, it turns out that this L function, or rather its analytic extension, still captures a lot of very non-trivial information about global structure of our elliptic curve. Hold on. So specifically, we have the following two conjectures, so they are still open. So if we consider this L function, we can consider it at point s equal to 1. And in this case, it can be either 0 or non-zero. And if it is 0, then it can be 0 to some degree. It can be a double or a triple or some other order of 0. And the conjecture is that the order of 0, order of 0 of L of E S at S equal to 1 equals, and this quantity should be equal to the rank of the set of rational solutions of E. So the thing with elliptic curves is that if we consider such solutions over some field, then they are going to form a group, and it is going to be a finitely generated abelian group. So in particular, if we ignore the torsion part, we can ask about its rank as a free abelian group. And this is exactly what we mean here. So the conjecture is that this order of vanishing of these analytical functions is equal to this algebraic rank. But while we are here, we are supposed to talk not just about this order of vanishing, but also about values. So it turns out that this, even if this order, if this quantity is, if this LE of S, LE of 1 is equal to 0, then we can still ask about the meaning of the first non-zero derivative of this function. So the conjecture is, so the second part of the, and this is the BSD conjecture, Bertrand-Sillerson-Dyer conjecture. And if you solve it, then you are winning $1 million. So if you have nothing else to do, then give it a stab. And the second part of this conjecture, which was also posed by Bertrand-Sillerson-Dyer, though it doesn't have a price tag of its own, is that if R is equal to order of this 0, then we can consider this quantity the R derivative of this function of E at 1 divided by R factorial is going to be, and again, this is going to be a bit of a salad of symbols, SHA of E. So I'll not write this down, I'll just say it out loud. SHA of E is a group called the Tate-Shafarevich group, and its arithmetic meaning is a bit weird, so I will not explain it here. It is not known to be finite, so finiteness of this is part of this conjecture, that it is finite, so its order makes sense, times R of E. So there's a quantity called the regulator. It is analogous to the regulator of the group of unions, and it measures how sparse the set of points of this elliptic curve is. And then we have something called the omega E, which is a certain integral over the real numbers taken over the elliptic curve. Then we also have a product of Tamagawa numbers over primes, which I also don't feel like really explaining, but it's supposed to be some kind of p-adic analog of this integral here. And we also have another factor, which is the order of the torsion part squared. So this equality, especially if you take R equal to 0, then it is supposed to be just some statement about the value of this L function at 1. It's in some ways analogous to this class number formula here. It involves quite a bit different quantities, but there are some analogies between them. For example, this regulator here and the regulator of an elliptic curve. And this order of the Tate-Shafarevich group is supposed to be in some ways analogous to the class number of our of an elliptic curve. So we see that, and again, let me just stress once again that this L function is built completely out of this local kind of data, and yet it is supposed to involve all of those kind of global quantities over the rational numbers, or over the real numbers here or over the periodic numbers here, which I think is something that is very interesting, and this is still something that is not very well understood. So those conjectures are wide open, especially for R when it is greater than 1. They are still completely open. But yeah, this is all I wanted to say. So thank you all for your attention. And if you have any questions, then I'm happy to take them. Or we can talk about them on Discord later. All right, thank you, Frog. Let me stop the recording.